You have a question? You there? Sorry. You have a question?
Sorry, what was that?
You have a question?
Yeah. So I was just working through some of the homework problems, and I came across one I was struggling with. It was in section 5.5, number 9.
All right.
Mhm.
And let me get my whiteboard out here. Well, let's see here. What do I want to do? I want to do this. Okay. Okay. So you said which one?
5.5.9.
5.5.9.
Mm-hmm.
Suppose that the length of life in hours, say X, of a light bulb manufactured by company A is normal with mean 800. And I'm assuming that that's sigma squared, right?
Yeah.
Okay, you always have to be careful about that, right?
Mm-hmm.
Distributed with mean. Okay, mu sub X is 800.
Mm-hmm.
And sigma X squared is 1,000 or 14,400. Okay.
Mm-hmm.
And the length of life in hours of a light bulb manufactured by company B is normal with a different mean. 50. Uh, 2,500. Do I have the right numbers here?
Mm-hmm.
Okay. One bulb is randomly selected from each company and is burned until death. All right. Find the probability that the length of the life of the bulb from company A exceeds the length of the life of the bulb from company B by at least 15 hours. Okay, so you want the probability that X is bigger than Y plus 15. Does that make sense?
Mm-hmm.
Okay. Or you could say this is the same as, this is the probability that X minus Y is bigger than 15, yes?
Mm-hmm.
But this is, right, it's equal to this. Well, what's the distribution of X minus Y?
Can we call it another variable?
Well, it's going to be normal
Mm-hmm.
with mean, and what you do is notice that this is 1 times X plus, -1 times Y, right?
Mm-hmm.
So this is that situation that I was talking about in one of the lectures where you basically have a constant combination of normal random variables, yes?
Mm-hmm.
So this is, remember it was the
Mm-hmm.
carrots problem or something?
Yeah.
So what do I have going on here? So this is going to be normal with mean equal to, so I'm just going to do those constants times the respective means. So
Okay.
800 minus 850, right?
Yep.
And what is, oops, not plus, comma. What is the variance going to be?
It would be the sum of the variances.
Right, so it would just be 14,400 plus 2,500. Okay,
Hmm.
so this is just normal with mean -50 and variance. Okay, what is this? 16,900 or something?
Hmm.
Which this has to be correct because that's actually a perfect square as well. So
Hmm.
that can't be coincidence, right? So let's see here. So I want this probability. Okay. So what? I can do that, can't I?
Hmm.
So let me see. I'll share. Now I can either go to Excel. Well, in fact, I would sort of have to go to Excel if I were going to. Can you see this?
Yes.
So the probability that X minus Y, is it greater than 15? Is that right?
Yeah.
Okay, well, first of all, it's probably easier to do 1 minus the probability that X minus Y is less than 15
Hmm.
because we're going to use the cumulate, right? And so what is
Yep.
going to equal? Well, equals, by the way, I could have converted this to the standard normal, but I don't have to do that if I'm using Excel, right? Excel just does that.
Hmm.
So if I use the normal distribution, oh, by the way, I need to do 1 minus, right? 1 minus
Yes.
normal distribution. What's my X?
15.
Yeah. Mean,
-50.
right? And now it wants a standard deviation.
So it's like 130.
Yeah. That's a square root of 16,900. And then it is that I want the cumulate, right?
Hmm.
The CDF. Can I get that?
Got it.
Uh, had you gotten that one before?
I think I had messed up my original my p of I had p of x plus 15 is greater than equal to y, so I think that's where I went wrong.
Okay, is that the right answer though?
Yes, yeah, that's right. And that
Okay.
makes sense.
Okay, and then the second problem says find the probability that at least one of the bulbs lives for more than 920 hours. Okay, let me just write this down. So X was distributed as a normal with mean 800. Was that right?
Yeah.
U was equal to 800
Mm-hmm.
and sig squared was equal to
Uh,
400.
14,400.
Okay, and Y was distributed as normal with mean 850 and sig squared equal to 2,500, right?
Mm-hmm.
And now I want to know the probability that at least one of the bulbs lives for more than 920 hours. So I want the probability that X is greater than 920 or Y is greater than 920, right?
Mm-hmm.
Isn't that just a union though?
Yeah.
Okay, so this is like, right, instead of or, I could just say, well, it's a union, right?
Mm.
And this is equal to, remember, probability that X is greater than 920 plus the probability that Y is greater than 920. But that will add the overlap
Mm-hmm.
twice. So what do I have to subtract off?
Their intersection.
Yeah, so it's going to be minus the probability that X is greater than 920 and Y is greater than 920. But X and Y are independent, right?
Right.
So like the probability of the intersection of those two events is just going to be the product of those probabilities. Do you know what I'm
Yeah.
saying?
Mm-hmm.
So it's going to be the probability that x is greater than 920 plus the probability that y is greater than 920 minus the probability that x is greater than 920 times the probability that y is greater than 920. Make sense?
Yeah. Gotcha.
So let me shrink this down so it's not blowing off the end of the screen here. Okay. So what's this equal? Well, let's first compute, okay, the probability that x is greater than 920. Well, that's equal to 1 minus the probability that x is less than 920, which is equal to what?
Use a standard normal.
Yeah, or just
the normal, yeah.
And the x is 920, the mean is 800, right?
Mm-hmm.
Standard deviation, what's the standard deviation of that thing?
120.
Cumulative, yes. Okay. And what about the probability that y is greater than 920? It's equal to 1 minus the probability that y is less than 920, which is equal to, so I don't know, normal distribution 920, mean 850, standard deviation
50. Yeah.
So to compute this thing, it's going to be to this plus this minus this times this. Is that the answer?
No, it's saying no, it's saying 0.2267.
What?
I think, unless I'm looking wrong. 5.5.9. Yeah. I think that's what the back of the book has. 0.2267.
Huh. Let's see.
What you did makes sense to me, though.
Well, look at, I mean, this, so 920. Wait, I think we did something wrong here. Hang on. Oh, this should be 1 minus this.
Oh, okay.
I was like, why would it be so high?
Right.
Mean is 850 and the standard deviation is small, right?
Yeah. That'd be pretty incredible.
That's that. So 0.2266.
Yep, that's it.
So here's another way to do it that's easier. I just realized. So so the probability that x is greater than 920 union y is greater than 920, that is equal to 1 minus the probability. So so the probability that x is either x is bigger than 920 or y is bigger than 920 is the opposite of the event where both are smaller than 920.
Yeah.
Remember De Morgan's law?
Yeah.
So A or B is the opposite of not A and not B.
And not B.
Right. So I could go, this is 1 minus the probability that x is less than 920. And y is less than 920. which, I mean, so Aaliyah, what is, what's that what's the probability that of that intersection?
It would be because they're independent, you can multiply the two, right?
Yeah. Okay.
Mm-hmm.
Well, now I can actually just straight up use the cumulates for both x and y. This would be equal to 1 minus normal distribution. So what is it? 920, 800.
120.
Yeah, 120
Mm-hmm.
times, I would have to multiply it by the other normal distribution, right?
Mm-hmm.
So 920, 850.
Mm-hmm. 50. And 1.
Yeah.
Nice.
So that's an alternative computation.
Cool. Well, cool. Well, thanks for going through that.
Yeah.
Appreciate it.
Everything else is stuff making sense?
Yeah, I was a little, I was gonna ask for some clarification on a little confused with the notation of like the constants and like the 1 over n. I think you said that they're like the same thing, like 1 over n is like C1 or C2.
Yeah.
I was a little confused there.
Well, I mean, so if n was like, 50,
Mm-hmm.
then that would be like a 1/50th, right?
Mm-hmm.
I mean, so you're confused about why if I divide by 50, that's the same as multiplying everything by 1 over 50? Is that what you're saying?
Yeah, I mean, maybe it was just because I was like looking at like the carrot problem or the one we just did where we multiplied by like 1, and it
Uh,
seemed, yeah.
yeah, so I mean, the whole thing is like you just have that 1 over n, right? I mean, basically, if I add up all the random variables, Aaliyah,
Mm-hmm.
divide by n,
Mm-hmm.
it's the same thing as multiplying that whole sum by 1 over n, right? So I mean, I
Okay.
can write this out right here. So note that if I go x1 plus x2 plus dot 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 plus xn, whatever n is, I could have of these things, and I divide that by n, yeah?
Mm-hmm.
That's the same thing as 1 over n times x1 plus x2 plus dot 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 plus xn, right?
Mm-hmm.
And then if you distribute that, that's the same thing as 1 over n times x1 plus 1 over n times x2, right?
Mm-hmm. Okay. So
1
yeah.
over n times xn. So if I compute the expected value of this, right? So, I mean, if all of those xi's have the same expected value,
Mm-hmm.
so if I compute the expected value of, well, here, let me actually copy and paste this. So I do the expected value of that, right? Oops.
Mm-hmm.
Shoot, what am I doing? Sorry. Expected value of that. And that's going to be equal to the expected value of that,
Mm-hmm.
which, by the way, I can write as, I can split up the expected value, right? I mean, I can just break that up.
Mm-hmm.
So then it's just going to be the expected value of, 1 over n times x1 plus dot 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 plus the expected value of 1 over n times xn. And what can I do with the 1 over n? Those are just constants, right?
Mm-hmm.
So isn't that just going to be 1 over n? And actually, I could factor out 1 over n from everything, can't I?
Mm-hmm.
So it's just going to be the expected value of x1 plus dot, 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 plus the expected value of xn, yeah?
Mm-hmm.
But if each one of those, let me kind of shrink this down a little bit. If each one of these things is just the same number, you know, like mu, right?
Mm-hmm.
This is just going to be 1 over n times, I think I actually have a mu somewhere in here. Is there like a symbol? There it is right here. Right, mu plus, plus dot, 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 plus mu. How many of those am I going to have?
Mu sub n. Is that right? Or?
Well, there was, how many were there right here? 1 all the way through.
Yeah.
There were n
Yeah.
of them, right?
Mm-hmm.
So there are n mu's added together here. Do you see what I'm saying?
Yeah.
There's a total of n mu's added together right there. So there are n mu's, okay, right there. So if I add n mu's together, that's
Mm-hmm.
going to be 1 over n times how many mu's?
N mu's.
Yeah, n mu. And what happens to the n's?
They cancel out.
Yeah, and you just get mu.
Okay.
So all that to say, this is x bar right here, isn't it? Very beginning, like this is what x bar was. X bar was equal to that junk.
Yes.
So what did we just show? We showed that the expected value of x bar is just the same as the expected value of the original things. Yeah? That kind of makes sense.
Mm-hmm.
The mean, right? If the mean of each one of the individual random variables is mu, and I take the average of a bunch of them, it makes sense that the new mean of that thing would still be mu.
Okay.
Okay?
Yeah.
But it also makes sense that the variance would go down because like the individual random variables are much more prone to fluctuating around. Does that make sense?
Mm-hmm.
Like an individual value is much more prone to fluctuating around, but when I start adding them together and taking the average, big things are going to be balancing out small things.
Okay.
So when I add those together and divide by the total number, I'm going to have a variable that's much less prone to fluctuating around. Yeah.
Okay. Mm-hmm.
So it makes sense that the mean would remain the same, but that the amount of fluctuation around the mean would decrease.
Yeah, that makes sense.
The variance ends up getting divided by n. You can go through a calculation kind of like this to show why the variance like sigma squared, whatever it was for an individual one before, for x, the new variance is sigma squared divided by n. Wasn't that in the lecture?
Mm-hmm.
The new variance was sigma squared divided by n.
Yeah.
So it makes sense that the variance is decreasing because big outliers are balancing small outliers so that the overall sum isn't as obnoxiously fluctuating around.
Okay.
Is that kind of helpful?
Yeah, yeah. Is that kind of like the idea behind this central limit theorem where there's like if there's more, they're like closer to the mean?
Yeah, that's exactly right. Yeah.
Okay. Gotcha.
What's going on is when you look at x bar,
Mm-hmm.
things that were obnoxiously big or small are balancing each other in the sum. Does that make sense?
Mm-hmm.
So that the distribution gets tamed. Before,
Okay.
you might have had some crazy. So the distribution starts to get tamed. It starts to huddle down around the mean.
Mm-hmm.
And and you get this nice normal distribution that starts to emerge. And by the way, the same thing is true even if you just look at the sample total. Okay?
Mm-hmm.
The sample total, Aaliyah, doesn't it make sense that that big outliers would balance small ones?
Mm-hmm.
And so you would still get a distribution that tends to normalize. Okay? And it kind of gets a more and more symmetry the higher the number of data points you take. That's going to be very, very critical for what we do at the end of the course. Central limit theorem is a very big deal.
Okay.
You can probably understand why, because what it basically says is it doesn't matter what the underlying distribution is. If you start looking at the sample mean or the sample total, if your sample size is big enough, you might as well assume the underlying distribution is normal, which is like, what? You know, that it wasn't
Mm-hmm.
necessarily. Well, it doesn't matter so long as you're looking at X bar or the sample total. So
Gotcha.
does that help?
Mm-hmm. Yeah. Thanks. Makes more sense. So like in that problem we just did, like the 1 and the -1, that was like in front of our x and y when we were like solving for like the new mu value, when we got like -50.
Yeah,
So those are considered the constant values in front of the.
right. Yeah, the 1 and the -1, yes.
And those come from 1/n, or that's something different?
Well, I'm only adding two things together here, Leah, right?
Mm-hmm.
So, I mean, the whole point here is, I mean, so this computation is just simpler. So I had, if I wanted to compute the expected value of, 1x plus -1y, how would you do it? Well, it would be the expected value of 1x. Let's not horse around here. That's just x, right?
Mm-hmm.
And then plus -1 times the expected value of y. So that'd be minus the expected value of y.
Oh, okay, so the n is how many you're taking from each individual distribution, not like the total number then? Because like, I don't know, I was thinking like n was 2 for some reason, and so then I was like a little confused, right? It was like
Well,
1.
so suppose x and y were both like normal with mean, mu and standard deviation, sig squared, whatever,
Mm-hmm.
right? Then what would be the expected value? What we're doing in the central limit theorem is we're not doing like x times 1 plus y times -1. What we're doing in the central limit theorem is something different. We're saying take x plus y and divide it by 2. Yeah?
Mm-hmm.
Which, what is that? That's the expected value of 1/2 x
Mm-hmm.
plus what?
1/2 y.
1/2 y. And then I break it apart, right? I can factor out the 1/2,
Mm-hmm.
the expected value even. So this would be, 1/2, and I could break apart the expected value. That would be the expected value of x plus the expected value of y. And so that's going to be 1/2. What's the expected value of x? That's what we called mu, right?
Mm-hmm.
And what's the expected value of y?
Mu.
Mu. Okay. And so what do we get here? This is just 1/2 times how many mu's?
2 mu.
Right, which is just mu. But that, right, the central limit theorem assumes that all of them have the same mean.
Okay.
Is that true up here?
No.
No, and I also was taking a weird combination of x and y. It was like 1 times x plus -1 times y. It wasn't 1/2 times x plus 1/2 times y. Does that make sense?
Mm-hmm.
Different situation when we're dealing with the central limit theorem.
Okay, that helps. Thank you.
But the procedure is the same. You just
Mm-hmm.
start and pull out the constants, yes? It
Mm-hmm.
happens to be the same constant, 1 over n in the case of the central limit theorem. And in the case of the central limit theorem, all of the variables x1 through xn have the same mean, mu. Yeah.
Okay. Mm-hmm.
So
Gotcha. All right. Yeah, thank you. That helps clear things up for sure.
okay, cool.
Appreciate it.
I don't know if you had a chance to see the lecture today yet. I don't know. Did that make sense or?
No, I haven't seen that one.
Okay.
I haven't seen that one yet.
Okay.
Yeah, I was just gonna probably finish checking the homework for the last lecture. Make sure that was kind of solidified before I move on.
All right. Awesome.
Yeah. Thank you. Thank you for
Yeah.
all your hard work and for your help.
Oh yeah. Yeah, no problem. And there's the quiz today, just reminding you. Or
Mhm.
that's due tomorrow.
Yeah, I think, yeah.
Okay. Okay. Yeah. Just as a reminder.
Thanks. Yeah.
All right. Well,
Awesome.
have a good afternoon.
You too. Thank
All right,
you.
see
Bye-bye.
ya.